Hi everyone, my name is Tia, and in this video I will be giving you an introduction to the tangent line. Learning about the tangent line is sort of like dipping your toes into the derivative pool. You open up a gateway to a lot more complicated but fun calculus. I'm super excited to teach this topic, so let's get right into it. In geometry, when we first learned about circles, we also learned about tangent lines. They are these lines that touch the circle at one point and are perpendicular to the radius. We can take this tangent line concept to the next level by applying it to curves. So, today we'll learn how to calculate the tangent line at a specific point on a curve. But first, we need to understand how secant lines behave. Secant lines are lines made by connecting 2 points on a function. As the second point gets closer and closer to the original point, the secant line begins to resemble the tangent line. So now that we understand what's going on visually, we can take a look at it mathematically. The equation of any line, including the tangent line, is going to be y equals to mx plus b. Our first challenge is to find out what the slope is. In other words, what m equals. In general, the slope of a line equals to f of x minus f of a, where f of a is the y value of the original point, all over x minus a, where a is the x value of the original point. As the secondary point, which is x comma f of x, gets closer and closer to our original point, a comma f of a, the slope begins to look like the slope of our tangent line. This relationship can be represented as a limit. The slope of the tangent line equals to the limit as x approaches a of f of x minus f of a all over x minus a. I suggest that you pause the video at this point just to ensure that you understand how all of these relate to each other. Let's do a practice problem together. We have the function f of x equals to x cubed, and we want to find the tangent line at 2, 8. I'm writing the limit definition of the slope on the top, so don't worry about memorizing it, but worry about understanding it. Let's just start plugging in what we know. We know that a equals to 2 because that's the x value of the point, and we know that f of a equals to 8 because that's the y value of the point. If you need a refresher on how to evaluate limits, I suggest checking out my previous video. So we have to do synthetic division because we can't just plug in the 2 or else our denominator will cause the whole fraction to be undefined. All of that simplifies to x squared plus 2x plus 4, and when we plug in 2, our slope is 12. Now that we have the slope, we have one major part of our equation, but we still need to find what the y-intercept equals to get our final equation. We know that the tangent line must contain the tangent point, so we can just plug in y and x and then solve for b, getting us a y-intercept of negative 16. So the equation of the tangent line at 2, 8 is y equals to 12x minus 16. There is actually a second limit definition, and that is m equals to the limit as x approaches 0 of f of x plus a minus f of a all over x. This definition is a little bit more mathematically intuitive rather than graphically intuitive. So this first term here, f of x plus a, as x goes to 0, this term approaches f of a. That means that it's getting closer and closer to our original point. The denominator, or the change in x value, is also approaching 0. Since the change in the x value between the original point and the secondary point is getting smaller and smaller, we can say that it's approaching the original point. So this definition works too. And in fact, overall, this definition is much more important because it paves the way for derivatives. So now let's take a more practical look at how the limit definition of a slope can be used. So here, d, the dependent variable, represents distance, and t, the independent variable, represents time. And if we take the slope of the curve at any point, we get distance over time, which is essentially velocity. So when we go ahead and apply our limit definitions to this, we get the velocity at a specific point or at a specific instant. So this is called the instantaneous velocity. Let's get into some challenging problems now. So we have the problem, find c and k so that y equals to cx cubed plus kx is tangent to the line y equals to negative 3x plus 4 at x equals to 1. Since we're given the line of tangency, we can extract the slope from it, which is the coefficient of x. We are also given the a value, which is just the x-coordinate of the point. Since we know the a value, we can just plug that into the equation of the line and find f of a, which is 1. We can plug in f of a and a into the original value to get a equation. This equation is important because it sets up a system that we can solve. Let's see if manipulating the limit definition in some way can help us find the second part to the system. As I write this out, we can recognize that we know a lot of these terms. For example, slope equals to negative 3, the a value is 1, f of x was given to us in the problem, and then f of a we solved for. And then that's all over x minus 1. Now we can do some synthetic division to get rid of the complexity inside of that limit. So we bring down the c, and that's the first coefficient, c is the second coefficient, and then we add it to k, and we get c plus k. But from our knowns, we know that that equals to 1. So we can go ahead and replace that with 1. And then 1 times 1 is negative 1, and we have a remainder of 0. So we know we did it correctly. Now I'll just give us a little bit more room to work with. So after synthetic division, all of that becomes negative 3 equals to the limit as x approaches 1 of cx squared plus cx plus 1. So at this point we can just plug in 1 for x because we don't need to worry about the fraction being undefined. And after that we can just solve for c, and we get c equals to negative 2. The problem isn't done yet though. We need to solve for k. We can solve for k using the equation from before. Since we know that c equals to negative 2, we have only one unknown, and when we solve for it, we get k equals to 3. So the original function should be negative 2x cubed plus 3x. Let's graph it though, to see if this actually works out. So I already have the tangent line graphed. Now I'm going to go ahead and enter the equation we got for the function using our c and k values. It looks correct because it's tangent at that exact point. Let's do another problem. Find all points on y equals to x cubed minus 3x where the tangent line is parallel to the x-axis. Well, first of all, what does it mean if a tangent line is parallel to the x-axis? If I go ahead and draw some lines that are parallel to the x-axis, we can see that the slope of all of these lines is 0 because there's no change in y value. So the slope of our tangent line also has to be 0. So we can go ahead and take our limit definition and set that equal to 0. F of a is essentially a specific value, so we can treat it as a constant and then perform synthetic division on it. So after doing all of that synthetic division, our equation becomes 0 equals to the limit as x approaches a, x squared plus ax minus 3 plus a squared. So now we can just plug a in for x because we don't need to worry about the denominator being 0 and the whole fraction being undefined. Now all that's left is basic algebra, and when we solve for a, we get a equals 2 plus or minus 1. We need to remember though that the problem asks us to find the specific points. Right now we only have the x values of those points, so we can go ahead and plug in 1 and -1 into our original equation, find the y values, and then we have our points. And there we have it, the 2 points on the curve y equals to x cubed minus 3x that have a tangent line with a slope of 0 are 1, -2 and -1, 2. Let's see how this problem looks when it's all graphed. So I'm going to go ahead and plot our points, -1, 2 and 1, -2. So these points are what you'll come to learn to be the local minimums and maximums. Now I'm going to go ahead and write the equation of the x-axis, which is just y equals to 0. Now I'm going to go ahead and graph the tangent lines to those specific points, and we can see that they're pretty parallel to the x-axis. So this means that the whole logic and reasoning behind how we solved the problem was correct. So I know this topic was kind of a lot, but it's so important that you sit down, you practice these skills, and make sure you actually understand it, because understanding this will make all of derivative calculus make so much more sense. And as usual, if you have any questions, please leave them in the comment section.